Okay. We're trying this again with take 3. Hopefully the audio comes through this time. Hi, I'm Mark with Advanced Assembly, and I'm here to continue voiding a warranty. You see, yesterday we worked hard to take apart my laptop, and we got some boards, and I'd like to look and see if there's anything that we can learn from those. But we have to do that in a manner that lets you guys see it, and lets our lab assistant, Chester, keep track of us. So, for that end, I have hooked up a new camera for us to on this little Amscope trinocular microscope. Last night I 3D printed a little mount for it. You can kind of see it right here. That should connect the camera to the telescope. It needs some adjustment. I mean, to give you some examples of the kind of video that I'll be able to show you, we just have to kind of be a little slower about it and a little more careful. But we should be able to get some pretty good images. Like right now we're seeing what appears to be differential pairs on this little guy. So we'll see what there is to see, and we'll go from there. One of the things I wanted to share with you that I think is pretty amazing is just how thin this particular board is. This one was in the back of the LCD screen, and if we pull this out, we've got about 23, I don't know if you can make that out, but we've got about 23 mils, which for our friends across the pond is just about 0.6 millimeters, I want to say. Yeah, just about a little shy. If I let it go, it'll open up. So anyhow, this is an incredibly thin PCB. The issue that you have with incredibly thin PCBs is that they're difficult to manufacture. They're difficult to jig and hold, right? They vibrate and mold. So oftentimes you have to do special processing for them. It's better, if you can, to make your boards just a little bit bigger. You know, if these guys would have added another 20 mils to their dimensions, it would have stiffened it up. It might have actually reduced cost. It's not true that, you know, always true that the thicker the board, the more expensive. Sometimes the thinner the board, more expensive. They did do some things I like. Look at the back of this bad boy. Nothing. All the assembly happened on the front side. All of the test points, everything. So we'll take a look at that one in a little bit. But let's start with the primary motherboard for this thing and see if there's anything interesting on it that we can make out. And for that, I am going to flip to our overhead cam, and we'll identify a couple things. This is our telecentric cam from high above. I mean, I love this thing. This thing's all sorts of fun. Got an IC that we can kind of see through, I mean, except for my smudgy fingerprints, but I think that's just part of the counterfeiting capabilities. I don't really know. Then we've got all sorts of connectors. This is where the main CPU went. And it looks like we've got some capacitors integrated right inside the housing there. And that is probably just to try to keep ground bounce low. Tell you what, let's start over in this area. We'll switch over to our microscope view, which is this one. So one of the things that I notice, and I bet you do too, is an absolute ton of holes over here. Now, I doubt those are signal. By the look of them, it looks like the designer just got a little happy with the copy-paste key and started stitching copper pores together. Depending on the frequency, the edge rates of the devices that he's dealing with, I think he went way overboard. You know, usually 0.5 not 0.5. What number am I looking for? 50 mil. Yeah, 0.05 inch. Usually that's pretty decent for a stitching pitch, unless you've got really high frequencies that you're dealing with. Isn't this thing fun? Now this is interesting. It looks like they've taken a differential pair and did they install test points? I'm looking at those two little blobs. The reason I think they're differential is because of the way that they're routed, nice and close together. Oh, you know what I bet that is? I bet that's a crossover. No? I don't know what that is. I don't know what they're doing there. That might be a crossover. No, it's not. I don't know what that is either. So, looks like they absolutely went nuts routing out this BGA. That must have been a headache and a half, man. Better them than me. But that's what you have to do. You have to find a way on the top layer or on adjacent layers to find each of those little balls, each of those little pins, and get an electrical signal out of it. The pitch, I guess while we're here for a second, the pitch matters, right? On a normal board, and this is, I'd say, relatively normal, it probably has around a quarter or half ounce copper plus plating, so, it gets a little higher. But your tracing space on half ounce is something like 3 mil for standard processing. Well, these things are so close together that by the time you get your spacing around those, you're only getting one trace out. Usually one trace between each ball. Sometimes you can get two. Here it looks like there's some balls that are missing to help facilitate the breakout. But you only get one. So you can start counting your way back from the outside to the inside as you do your layout. And each layer you go down one more, and you figure you get one trace per layer, but then the balls are gone, so then it starts to open up a little more. But you can figure out how many layers you need from the pitch and the size of your ball grid array. That really dictates it. So if you're ever in a position to choose a BGA with a larger pitch where you can get two traces out, you can more than half the number of layers that you need in your design. So small pitch BGAs, they're a pain, but they're also a pain to route and assemble. So this is kind of fun. I'm just kind of looking around, seeing if anything catches my eye. We're going to zoom out a little and see if I can grab focus on it or not. I don't know that I can. I don't know what I'm doing. That's clear. Okay, just had to make a bigger movement. But did that let me see more or less? I don't know. I guess a little more. It's just a little more out of focus. Oh, okay, just can't get that zoomed out. All right, that's cool. Some of the interesting things are where they decide to pour copper and where they don't. Here, oh, come on, don't move on me. Stay right there. Here we're looking at a layer of copper through the fiberglass, right? These layers are really close together. And you can kind of make out the spot where it transitions there. Let me see if I can't find something to act as a pointer. Okay, so right here, this bit of copper that's on the surface transitions via two vias underneath the surface. And this is actually giving us the resolution 2 that you can see the warp and the weave, or the weft, of the fiberglass. All those little points are spots where it goes up and down. So if we can follow this, we see that it kind of Y's out and goes off there somewhere. And then it stays underneath, gets pretty close to that that through hole, and it runs down over here. Looks like it goes under, and then I'm going to lose it. Yep, I don't know what happens to it at that point. But on this side of the board, they've elected not to do copper fills, and I don't have an answer as to why. Sometimes you have to worry about copper becoming unintentional radiators on your board. But the other thing you have to worry about is fabricators. They like copper. That's just what they do. And they'll put copper thieving on your board if you don't tell them not to, just so that they get a better, a better plating experience, a more uniform plating experience. Okay, so now I want to transition over to this chip if I can find it. Oh, where are we? We're scanning. Ah, here it is. Let's see now. Let's see if I can get into the middle of it. So I definitely need a little work on my microscope skills. One of the issues that I have is that I can't look through the eyepiece and have the microscope going at the same time. It's completely out of focus. And the zoom rates are radically different for the eyepiece and the thing. Okay, so now we're looking at a chip that is actually mounted on a carrier board, right? This looks like a PCB. Here's the motherboard, right? You can actually see a little stretching in the underlying fabric. That's interesting. And here's another one, and you see vias, and you see traces. Let's see if I can get a little better focus for you. Right, this is unimaginably small. I don't know how to convey that to you other than, let's see if I can do it with the I'm going to see if I can do it with the micrometer here, or the caliper. I'm going to see if I can. I have it set to 10 mils, and I'm going to see if I can. Uh-oh, it's not going to fit. No, come on. So I've got to zoom out ever so slightly just to fit the calipers underneath. Okay, so the calipers are a little bit above, but I've got them set to 10 mils of separation, just to give you an idea of how small those traces are. Sorry about all the movement there. Hope you're not getting car sick at home. So those things are small. Those are 2 or 3 mil traces. I'll have to do a little better job of aligning the camera and everything for next time, and figuring out how to keep things from moving so much. They should lock off, and they're not. So I'll look into that for you. But anyhow, one of the things that manufacturers can do is actually permanently glue, not really glue, there's a process, 2 printed circuit boards together. So if you have something that's small and delicate, and you need it to get on the board and stay there permanently, they have this stuff called Transient liquid phase sintering paste. And the way that it, oh, that's cool looking. The way that it works is you have 2 boards, and you have metallized contacts between them, and the paste goes on, and when it reflows, it actually forms a metal. The molecules, when they combine, the paste with the metallized pads, they form a new metal whose liquidus temperature shoots up, something crazy like 800 degrees Celsius. So you put this stuff together, you put it in the oven at a relatively low temperature, say, and I don't know what that is off the top of my head, let's call it 270 degrees Celsius, a little hot. But you put that in, and new molecules form that have a much, much, much higher transition temperature. So once you put this stuff on, it does not come off. And you can use that to make parts of your stack up larger if you need to. But tell me that's not a cool picture. And what it looks like we're looking at, amazingly enough, are differential pairs that are crazy close to each other. Let's see if we can do anything on the zoom for that for you. I don't know if I need to. Oh, I probably lost my alignment again. Let's see if we can. I don't know. I think my microscope skills need some work. Doesn't help that this thing's cantilevered out as far as it is. But where did our pairs go? No. Yeah, those have to be differential pairs. We just can't see them close enough. But those are unbelievably small. I mean, you would measure those things in microns if you could measure them at all. I can't, on my little monitor, I can't tell if we're in focus or not. It looks like it. But isn't that cool? Now, you'll notice that they ran some extra distances around there, right? Some of those traces are quite obviously larger than they need to be. And the reason for that is about timing. The designer here felt that the variable trace length would cause the rise and fall signals, the logic level transitions, to appear to the chip at a different time. And the faster that you go, the more critical this becomes. So I'm looking at, it looks like 8 sets of differential pairs. So this is probably, and this is a guess, a parallel data bus that's delivering information somewhere else. That would make sense to me. It would also make sense as to why you need all of those traces to have equal length. And even if they don't have equal length in this section of the board, I assume that they have equal length, when you take this in combination with the other stuff that was designed. So, interesting. Sometimes you see engineers do this too when they just don't need to. Their timing budgets, their SKU budgets are, they're going for perfection when they just don't need to. Here's more differential pairs. Let's see how many we have there. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I lost count. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, it looks like. Golly, those things are small. So I am glad I am not a board designer. All right, so here's a problem for people where machines really shine. What we have here, we're looking down at a partially populated either resistor or capacitor array. I don't really know which. Not by the looks of things anyway. But look where they are and look where they aren't. Right? Some of these didn't get populated. Can you imagine being a human trying to figure out what's supposed to be there and what's not, looking for mistakes, looking for things that got misplaced? You would have to know all that. It would take forever. But if you throw this into a AOA machine, AOI, Automated Optical Inspection, it can really just crank right through that stuff. This I like. This trace is a little thicker than the others, not by much, but it is. I'm suspecting it's a power trace. And one of the nice things about doing it in a Y rather than just doing 2 corners, that meet at a T, is thermal considerations. Now, I doubt they're running enough current through this to matter, but it's still a decent design practice. But when you have the traces like this, it captures more area for the heat to spread out. Right? If you have it in a T configuration, the heat gets concentrated at the inside corners of the T. Here, it gets a chance to spread out everywhere. So, was it necessary? No, probably not. But from a thermal design point for power traces, it's a good practice to get into. It's certainly not going to hurt anything. So we've got more components of various sizes. Sometimes you have to choose those based on availability. Sometimes you choose those based on the characteristics. Different sized capacitors, for example, will have different dielectrics inside of them that have different properties. And the little tiny ones are the COG X7Rs, X5R type stuff. Lower inductance, which is something that you want in high-speed design, while the bigger ones usually have greater capacitance, but they really die off thermally. All right, here we are at the edge of the board. It looks like they kept their copper back a decent distance, and if you look at this edge, you see why that's important. Right? The copper needs to be kept from the edge of your board at least 12 to 14 mils, because when you break it out, you never know when you're going to get a slight goof or, like we saw earlier, quite the uneven edge. If you have copper running up to the edge, that is just begging for a short circuit. Now there's a big trace. That's running some current. We're seeing a meander. Again, this is a length matching tool that tries to get the data to all show up at the same time. Oh, got a kitty here that's mad at us. Okay. It's kind of interesting. Kind of not. Kind of fun. I know, Chester. I know. Well, I think that's about all I want to look at on this particular motherboard. We can take a moment and glance at the back. There are some things I want to show you on the connectors that I think are rather neat. We're looking at the backside of a BGA that got broken out. It's a lot of stuff. A lot of. This is the backside of, where are we here? This is the backside of the CPU. Again, something that had to get broken out. And it's just cheaper to go through hole if you can. There are some high density interconnect methods that you can do to get away from that if you have to, but do it if you can. All right. Let's switch cameras and move to our connectors. So they did something here that I thought was pretty clever. I don't do it myself just because of it. Usually the expense doesn't warrant it, the extra work, but it's totally doable. And what I want to show you next is what's going on with these connectors. So let's get to our down cam and get you a little better focus. Boy, I tell you, I need a video crew. All right, so this is what's unusual about these connectors. If you notice, they all end up in the plane of the board. This is really a height shaving item, right? We've got HDMI, RJ45 jack, DB, is it a DB? No, it's a D sub 15. I forget if it's a B or E shell enclosure. It doesn't matter. It's a sub-miniature enclosure. But look at these things. Every single one of these is designed to be in line in the plane of the board. How about that? And it's possible, I mean, we can do some desoldering here in a minute if you want, but it's possible that it is actually part of the board. We would have to go in and look. But how cool is that? I don't even know how much those things cost. I'm sure it's expensive. Plenty expensive. But these things just solder right in. I think, you know something? I think we should turn on the heat gun and see if we can't relieve some of those. What do you think? Are you up for a little bit of noise? Let's find out. All right. Heat gun on. Probably could do with a larger head. But we'll start small, we'll go big. So this is just part of my hot air rework. We could put a little extra flux on here to make it easy, but honestly, I don't even know where these things are attached at this point. So we might just be causing a mess. I don't know. So right now, I am just heating up. We'll come back on the down cam here for you. So I am just going to apply some gentle heat. Boy, I tell you, I need a... let's get this out of the way first. I need a camera guy. Somebody that does all my focusing and whatnot for me. We'll have to look into that. What can they cost? $3 an hour? Right? No. Come on, big guy. Might need to oh, that's why my heat is set way too low. It's probably a safety feature. There we go. We'll give that a moment to warm up. Okay, that is pretty warm. We're going to test it out on this cap first. I'd like to see that liquid transition. If we're dealing with Rojas, I need to crank the temperature up even higher. Yeah, I should have melted something by now. Yep. See? Just getting stuff too hot. We need more active temperature here. Let's go higher. I'd worry more about this stuff if I was keeping it around, but I'm not. So all I'm doing here is trying to get a little bit of heat around here and seeing if this thing will start to move. I don't even know what direction it pops out, to be honest with you. Apparently that direction. All right. There's one. I'd be better off with a slightly larger nozzle, but I'm lazy. So I am applying a ton of heat to this board, but I am not seeing the solder transition. I'm actually at risk of delaminating. I'm certainly decomposing the glass. It's going to start smoking here in a minute. So we'll give that a break. Maybe I need to hit it from the other side. I don't know. Let's try a different one from here. It could be that these things have little extruded pin holes holding them in, and I need to get all those free, in which case I'm not going to do it, because I don't want to pull out the flux and make a mess. Just to mess around. I sure would like to see that solder transition before I reach the glass transition temperature. There we go. Come on. These are not practices that you would want to do if you were trying to save this board. But I find a good whack will release a lot of components if the solder's hot enough. But here, I'm just melting it. I'm not doing anything useful. Alright, we'll let that cool down. That is plenty hot. And we will look at what we have. Let me grab see if I have a set of tweezers handy. I imagine those are still smoking hot. You know something? Let's do this. See if we can find this guy on the camera. I'm looking at my mat. That's not exciting. Come on. There, oh, there it is. Okay. So this is our audio, and it looks like it's got some retention clips. Might have been one of the things I was fighting. So this just slides right into a slot, and the pins grab into the edges of that slot and hold it in. That's your audio connector. VGA. God, I did a bad job. Oh well. Your VGA connector, you've got, it sits flush with the board, and all of these pins just go in and grab stuff. Okay, you don't have to say it. That wasn't as fun as I thought it would be either. I'm with you. But let's keep cranking along, shall we? While we have it here, we've got memory. Usually something that requires a bit of skill to work with, to route. Really, really tiny traces, man. That stuff is thin, thin, thin. I've really got nothing to say here. I mean, when you're doing a board with fingers, you have to run your copper right up to the edges, you know. Talk to your manufacturer, see what they have to say. And then sometimes they have to shave the board down, you know, put a bevel on it, which means that's going to affect your arrays, because you can't bevel the inside of a board. You can only bevel the outside of a board. So there's memory. I mean, everything's hidden from view. We can't really see what's under those chips. You'd have to get an X-ray machine. I might save one of those for the 3D X-ray next time I see it. That could be fun. This little board came out of the computer too, and the thing that I was struck by is this particular IC by LAN. Let's flip that around. LAN, I haven't heard of that. But this thing's got a crazy aspect ratio on LGA or BGA leaded part. So that was kind of interesting. And then let's see what we want to look at next. This one is our CPU. And you'll notice that this has the same thing going on as the last one did. It's a, it's its own carrier board. It's its own printed circuit board. And it's got all of these incredibly small, and I can't make it out on my monitor, but just based on what those vias are doing, those sure look like differential pairs to me. All right. As we continue on, what do you say we cause a little trouble with this bad boy? Let's get you on the overhead cam. This is the hard drive that came with everything. And they usually have some amount of ways to discourage you from opening them. Security bits, whatever. It's possible that I don't have the right security bit with me at the moment. Let's see. It's a little small. Way big, I'm sure. Way big. Way small. Ooh, feels pretty good. Let's see if it'll turn. Oh, I've got the bits. What did I do with Mr. Screwdriver? That's the question. Oh no. That will make my job slightly tougher. But I've been accumulating a mess here, and now I'm paying for it. So I am just going to put this in my vamp pliers and get all of these broken. I know the world's moving towards solid state drives nowadays, SSDs. Maybe we'll open up one of those one of these days. But on all of the old hard drives, I mean, without fail, all of the ones that I've ever taken apart have a hidden case screw that you can't get to without breaking plastic. And sometimes you have to cut it away. Sometimes you can just poke through and grab it. But almost, I mean, watch this be the one exception. But almost without exception, there's a hidden screw that you have to deal with. And there it is. I really got to get my microscope game going a little better. Okay, where are we looking? Is that it right there, centered? Right in the middle of the... There we go. So we've got this screw that's hiding underneath the plastic there. So we'll break that one too. And all I'm going to do, all I have to do is just loosen them. The rest of this will... Oh, I see the screwdriver now. Of course I do. So now we can just spin all these out. The moment that you do this, the moment that you open up the hard drive, you've contaminated it, and it is not long for this earth. I remember way back in the day, I don't know, late 80s, early 90s maybe, but somewhere back in there, I went to a computer repair place, and back then, data was stored in such a large area of the hard drives that they could, in a controlled environment, actually open the hard drive. When it failed, they would open the hard drive, and they had tools that would go in there and then reread the platters. I'm sure you can't do that today. I don't know. Maybe the NSA and CIA and whatnot have tools for that, but it would be incredibly difficult. It is in such a compact area that you just can't do it. Okay, so here is our hard drive that will never work again. And it's, it's simplicity itself. You've got a really, really strong magnet. It's actually two magnets that surround a... Let's see, is there a screw to... Oh, there's a screw to come out. But you've got these two strong magnets that surround a special coil of copper. And depending on how they run current through that copper, so here's our magnet. It's a rare earth magnet. These things are really handy. I always take hard drives apart just to get to the magnets. And then you've got this coil of copper that moves back and forth in the magnetic field. And it can use that to position it, like a little itty-bitty stepper motor. Well, kinda. That might be too broad a generalization. This is a bearing, and the magnet is attached to this lever arm that pivots on the bearing, and then wires go out to, I broke one of them, oh well, to these little read head, these little sensors. And the sensors work off of, I forget for hard drives. Do they use giant magnetoresistance? I'll have to look it up. I don't want to lie to you. So each one of these is going to be reading one side of the platter. And since there's 4 total, that tells me that there are 2 platters in here. And the platters store the information. I mean, as everything spins around, those bad boys have magnets stored in all sorts of different directions, right? That's what all of your data is stored on. These little guys, or at least used to. Now we're moving towards solid state drives. But it is amazing stuff. And the speed at which it spins is controlled by a stepper motor. Why it's a stepper motor, I couldn't actually tell you. I guess just so they get the speeds just right. That one doesn't want to come out. And that's not the right size to make it. There we go. Okay. So, you know something? Let's go single source again. So there's our hard drive internals. You know, we've got the motor that spins everything around. It's a stepper. You've got really strong magnets, which is what I'm after. But yeah, if you ever have to open up your hard drive, or you think you have to open up your hard drive, don't open up your hard drive. It's probably toast, and if not, you need to send it to some people that have a clean room that can get in here and, you know, swap out components that you might need to get the thing running again. Use probably just the logic board. Anything else, and you're probably pretty well screwed. So there's our hermetic connector. Who knew computers were this much fun? And then, while we're at it, we're just going to keep bumping along here. At this point, we might as well just take it all apart. Interesting thing here is that there are no components exposed. They are all going to be hidden on the other side of that board. And that's pretty handy. I mean, less things to get broken, right? And then, if they design it right, the cavity is close to the components. They can use the cavity as a heat sink. And it looks like they did. So this is the logic board of the hard drive. And they have it engineered with all of the parts on one side. Great design practice if you can get away with it. It'll be much cheaper for you. And then all of these components contact the metal board for cooling. I mean, I don't know what the three of these things are, but based on their size, they are, you know, powerful. They've got lots of in and out pins. Usually means there's lots of processing power. So I didn't know that there were that many in these little hard drives. It's pretty amazing. And there are some interesting things about the layout there as well, but we can set that aside for now. Boy, I tell you, we're taking apart all sorts of things. Okay. What's next? What's left? My goodness, we have had the day, haven't we? Well, I think we've looked at the board sufficiently, for now anyway. I'm sure there's more lessons we can learn, but it probably requires me doing a little bit of homework and marking some spots, flagging some spots. Oh, I know what we have next. Ha ha ha. Check out this guy. All right, so before we do that, let's do a little bit of cleanup so you know what you're looking at. This is getting a little bit much to keep track of. So for now, just for now, I'm going to put all these screwdrivers back. I had a nice little 3D, well, it was actually a laser cut case for these. And it broke one day, so I need to make another one. But it's a dandy little set, I'll tell you that. While we are waiting, though, we have Chester here, who's come to inspect things. This is our friend Chester Cat. He's a nice kitty. He's mad right now. At what, I don't know. But he's voicing his displeasures. Oh, we're going down. He must be hungry. Okay. Chester's getting a little older, a little grumpier. probably doesn't feel so well. So if you will indulge me just a few minutes more, we're going to get this area cleaned up ever so slightly, and then move on to this. I think we're done. I'll keep the boards, but we are done with the mechanicals. So that can find its way to recycle heaven. We've got our stainless hardware there. We are going to get all of these out of the way so we don't confuse them. That all is trash. Trash, 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 trash. All these little screws, I don't know. Okay, so moving on with our super fun, we've got a DVD. And you know something? I'm going to use this opportunity to go off air in the stream and start it again after I grab something to eat and maybe give Chester a little something to eat. So with that, I would like to thank you for joining us today. As always, if you ever have questions, comments, concerns, you want to learn more about PCB design, please visit aapcb.com. And if you have questions, just email sales@aapcb.com, and we'll do what we can to help you out. Take care. I'll be back in about 5 minutes.